So for the picket fence experiment, you've got three pieces of equipment. You've got a piece of foam and a picket fence, which is a plastic sheet that has black stripes on it and clear stripes on it, and also what's called a photo gate, which is this little device here. A photo gate basically has an LED over on one end, which is sending out an infrared beam, and then a detector on the other side. So that means that the computer can sense when the beam is blocked. So what we're going to do is, first of all, you take the foam and put it on the ground so that when you drop the picket fence onto it, it doesn't shatter. And we're going to start our program called Freefall, which I'll show you in a moment. And we put the photo gate sideways on the table like so, and then we will start the program, drop the picket fence through the photo gate, and because there's black and white stripes, we're alternating blocking the beam and not blocking it. The computer's going to be able to figure out what the velocity versus time graph should look like, and from the slope of that we should be able to get the acceleration due to gravity. Be just in the loose files, so go to Freefall and open that up. Once you've got your experiment set up, you're going to drop your picket fence through the photo gate, and I'm going to show you now what that looks like on the graph. So to begin with, you would click Start up here at the top, and then very quickly drop your picket fence through the photo gate. So I'm going to do that right now. You may need to click Stop to get the data to stop taking, and we want the fit for this. So my data looks a little weird, so I'll go and turn off linear fit and then turn it back on again, and now it gives me a slope for this line. And of course for freefall, the acceleration, this is a velocity time graph, the acceleration should be equal to gravity. So you should look at these values and decide whether that number agrees with the acceleration due to gravity near the surface of the Earth within uncertainty. So for the first time this semester, you're going to have to write a conclusion. Most of the experiments we do this semester will have a conclusion that you need to write. Near the beginning of the semester, they give you this bullet list of things that go into the conclusion. So I'm going to go through this very quickly right now just to give you a good idea of what each of these things is. It's question 4 in your lab manual if you want to follow along. The first thing they ask for is they tell you, state the objective, what were you trying to measure, and what is the hypothesis for this experiment. So the objective is just what it says. What were you trying to measure? So for example, for the freefall experiment, we were trying to measure the acceleration due to gravity. So you would just say that in a full sentence. We were trying to measure the experimental acceleration due to gravity. What is the hypothesis for this experiment? Hypothesis is usually just going to be some variation on we expect our measured value to agree with the predicted value within uncertainty. So for most experiments, that's what you'll write, something like we expect our measured acceleration due to gravity to agree with the known value within uncertainty. The second thing that goes in the conclusion is they say state your values, state your measured value and your predicted value, and include their uncertainties and also their units. So again, in a full sentence, you just write it out. My measured acceleration due to gravity was, give your number, plus or minus 3%, make sure you put in units. And my predicted value was, and again, you put in the known value, 9.81 meters per second squared, plus or minus 0%. The third thing you put in your conclusion is they say state the percent difference between these values. Now that's a calculation you've already done at this point. When you get to your conclusion, you have this number. So again, you just write it down in a full sentence. My percent difference between these two values was, and you give your value. The next thing you need to do is you need to state whether your values agree with an uncertainty. So this is sometimes a little confusing. You've got a percent difference that you just calculated. That is the difference between these two numbers. It's a way to gauge how far apart they are from each other. The uncertainties, which you also have, are a measure of how big a difference you're allowed to have and still say that your values agreed well. So the way in which you compare two values is you look at your percent difference that you calculated, it's a percentage, and you look at the sum of the uncertainties for the two numbers. So you look at the uncertainty for your measured value, which in this case was 3%, and the uncertainty of your predicted value, which in this case is 0%. You add those together, So we get a total of 3%. We don't want our percent difference to be any bigger than that. If the percent difference between these two numbers is larger than 3%, that means our values do not agree with an uncertainty. So you look at your percent difference and you decide whether it's less than the combined uncertainty of these two numbers. If it is, then you say my values agreed with an uncertainty. And if it's not, you say my values did not agree with an uncertainty. And it's a good idea to write down your logic, just to say because this number is less than the sum of these two numbers. The next thing you talk about is whether the theory is supported by your data. So basically, if your percent difference is less than the sum of the uncertainties, if your values agree with an uncertainty, that is, then you can say that yes, the theory was supported by the data that you measured. The last thing you do is you have to identify what's called the largest source of uncertainty. So there's an acronym that they use, LSOU. And the largest source of uncertainty, it depends on whether your values agreed or disagreed with an uncertainty. So there's this acronym that never gets defined anywhere in the manual, VAWU, V-A-W-U. That just means values agree with an uncertainty. So if your values agreed with an uncertainty, then your largest source of uncertainty is something you took into account, something you already knew about. So you would go back to your data table and you look at the percent uncertainties on all your raw data. Whichever one is biggest, that would be your largest source of uncertainty, but only in cases where your two values agreed with an uncertainty, where the percent difference was smaller than the sum of their uncertainties. If your values did not agree with an uncertainty, then the largest source of uncertainty has to be something you didn't take into account. So it might be friction or air resistance, or maybe there was something weird about your equipment. But if your values don't agree with an uncertainty, then you have to suggest that your largest source of uncertainty was something other than the uncertainties you took into account on your raw data. So if the values agree with an uncertainty, your largest source of uncertainty is one of your percent uncertainties on the raw data. And if your values did not agree with an uncertainty, then the largest source of uncertainty has to be something else, like friction or some exterior force that affected the experiment. Okay, now we're going to look at the 3 simulations that there are for experiment 3. So as usual, go into the 1100 folder, go into the lab 3 folder in there, and you'll find 3 simulations. So let's open up the first one. What this is we're going to press run, and it's going to run a little movie for us. So what we'll see is that there's 2 balls here. One of them will be dropped straight down, and one of them will be fired exactly horizontally, and then we'll see how they fall. So I click run, and I'm stopped as soon as it bounces. We don't really want the bounce. And it's a little confusing to look at, but they show you the velocity components and the velocities of these 2 balls as they're falling. If you decide you'd like to rerun this guy, you go reset, and there's an unfortunate hiccup in the program in that it doesn't get rid of all the rest of this junk. So to clear the screen, you want to go Control H. That gets rid of it. So Control H if you want to reset so that the screen looks nice. So again, run, and I can stop it as soon as it bounces because we don't care about what happens after the bounce. So they tell you that you can sketch a stop action picture. In other words, sketch what you see on the screen. There is also an easier way. If you look on your keyboard up at the top, there's a button that says Print Screen. If you click that and then open up Word and then go Paste, and I think you can just go Paste, regular, and it will put it in here, and then you can print out 3 copies for you and your partners. So that's a lot easier than just sketching it all. So go Print Screen on the keyboard, and then open up Word, paste it in, and then you can print off as many copies of that as you want. I'll close that because I don't actually care about it. And we go back to the simulation. So they ask you a bunch of questions, like what would happen to the horizontal and the vertical velocities of these 2 balls. You can look at the screen to read that. So you answer the questions, and then when you're done with that, you can close this guy and open up the next simulation. So as normal, you close it, they say, do you want to save the changes? Just say no. So open up simulation 2, and now we have a ball that's going to be fired into the air at an angle, and it'll come back down. So I'll run the simulation, and I'll go stop as soon as it bounces because we don't care about that. Another little hiccup of the program is it didn't draw the first one for me, and I kind of would like it to. So I'm going to hit reset, just because then it redraws this guy here, and I've got a much nicer picture. So as before, you're supposed to sketch this, and it's easier to just go print screen, open up Word, paste it in, and then print out some copies. And again, they ask you some questions, like what happens to the velocity of the ball as it's rising, what's true at the top of the trajectory, and they say draw 2 to 3 conclusions relating to velocity and or displacement and or time at the end of the trajectory, so at the end here, just before impact. So this is stuff that you would answer based on what you've learned in class, and you're basically looking at the symmetry of the situation. So what can you say about the time, say, to get to here relative to the time to get to here, for example? What can you say about the vertical or the horizontal displacements? Stuff like that. So just talk about what you've learned in class, and tell me what's true at the end here relative to other points in the trajectory. Then you can go on to simulation 3. So again, I'll close this and say no to changes. Open up simulation 3. And this is very similar in that it's going to fire a ball up in the air at an angle, and it'll come back down, except it's going to come back down lower than it was fired off. So again, run, let it come back down, stop it when it rebounds, and because it doesn't draw this first one, I'll hit reset just to give me a nicer picture. If you want to redo it, again, you can go reset and then Control H to clear the screen. So let's run that again. And now we have a nice picture, so print screen, put it in Word, paste it in, print it out as many times as you need to. And they ask you some questions about that. So where is on the trajectory, is the speed equal to the launch speed? Where is it less? Where is it more? You do not need numbers off of the screen to answer those questions. It's something you should be able to answer based on what you've learned in class. And once you're done that, then you can go on to the next part of the experiment where you will actually be firing a Hot Wheels projectile into the air and taking measurements from it. In this part of the experiment, you're going to actually use a Hot Wheels car as a projectile, and we're going to fire it through the air and see how far it goes. So on your table, you've got a brick and also a section of Hot Wheels track, and you take the track onto the brick and also onto the edge of the table to make a nice ramp. And then the Hot Wheels car will just slide down this ramp, like so. Now, we're going to measure, the point of the experiment is to measure horizontally how far it goes. That's called the range. We're also going to calculate that value. So in your lab manual, on page 48, there's a table, and there's 4 things that they tell you to measure. The length of the car, so that means just the length of this guy from end to end. The height of the table, which you can measure with the meter stick you've been given. And the photo gate time. What's that? Well, here at the end of the track, we've positioned another photo gate. This is oriented in such a way that when the car goes through it, it blocks the photo gate. Now remember that a photo gate is just an infrared beam and a detector, so you can that allows a computer, or in our case a little measuring device, to measure how long it was blocked for. So we're going to measure how long the car blocks the photo gate beam for. The timer that we're using should be on gate mode and on read mode, which means that the little lights should be on. If you need to reset the value at any time, you hit the red reset button, and it should zero everything for you. And you can test this. What should happen is if you wave your finger through the photo gate, a number should come up on the screen. If you wave it through a second time, nothing should change. So it just stores the one value. And again, if you want to zero it, just hit reset. Now the reason why we need these first 3 things, the car length, the height of the table, and the photo gate time, is so that we can calculate, theoretically, what the range of this Hot Wheels car is going to be. And then the last thing we measure is the actual range, so the experimental value goes here at the end. These 3 are going to be used to calculate it. To get the reason why we measure the length of the car and the photo gate time here at the beginning is because we need the velocity of the Hot Wheels car as it's leaving the track. So velocity is just distance divided by time, right? So this distance, the length of the car, divided by the time that it blocked the photogate for gives you the velocity. So just distance divided by time gives you the initial velocity of this guy. And we use the height to calculate how far it would fall, or how long it would be in the air if we just dropped it from the same height, which of course we can use to calculate how long it's in the air for, even when it's going horizontally initially. So I'll tell you about the equations used in a second. The last thing I want to tell you about is how do we actually measure the horizontal range of this guy. What I recommend you do is run the Hot Wheels car through this, see where it lands on the floor, and then you've got a piece of carbon paper. Tape that to the floor in such a way that you can flip up the carbon paper and see the dot that the car makes on the ground when it hits. So you tape this onto the spot where the car is going to hit. You zero your photogate, run the Hot Wheels car through there, it hits the paper, and then you can flip back the carbon paper and use your meter stick to measure how far it went from the edge of the table over to the dot on the page. So that's how you get all of your experimental values. And as I said, I'll show you in just a moment some things to be wary of when you're doing your calculations. So now I'm going to talk about the equations that you use in this experiment. So the first thing you'll calculate is the launch speed of your Hot Wheels car. So how fast was it going when it left the track? And as I mentioned earlier, it's just going to be the length of the car divided by the time that the photogate was blocked for. So velocity is equal to distance divided by time. The next thing you calculate is the time of flight. This is how long it's in the air for. The way we get this is we know from theory that the time of flight, if you launch the car horizontally and just let it drop under gravity, is exactly the same as the time of flight would be if you dropped it from that same height. So we calculate that, and you have to be a little careful here in that d is equal to the height of the table here. So it's changed its definition relative to what it was up here. So up here d was the length of the car, down here d is the height of the table. So the time of flight is going to be 2 times the height of the table divided by the acceleration due to gravity, all square rooted. Once you've got those two quantities, you can then calculate the horizontal range. So this is our theoretical horizontal range. This is how far we figure the car is going to go. Again, d changes its definition, so it's something to be a little careful of when you're doing the calculations. Over here, d was the length of the car. Down here, d was the height of the table, and over here, d is the horizontal range. So just be careful to keep those straight in your mind. But this horizontal range is simply going to be v times t. So this v that we calculated times this t that we calculated. So launch speed times the time of flight gives us the horizontal range. So after you've gotten these quantities, you're also going to have uncertainties that you've calculated for all of them, and then you proceed to something that's going to become very familiar over the course of the semester. And that is, once you've got your values, you summarize them in a table. So you'd write down your values here with their units, plus or minus their percent uncertainties, and you put a title on the table that's worth marks. So you summarize everything in your table, and then next you would calculate a percent difference between your two values. So you've got a theoretical value that you calculated, you've got a measured range for the car that you measured with the meter stick. So you compare those two, calculate a percent difference, and once you've got that, you could then proceed on to write up your conclusion. So remember that your conclusion consists of answering all of these points in your bullet list. So state the objective, what were you trying to measure? In this case, it was the horizontal range of the car. What's the hypothesis? Basically that the measured value is going to agree with an uncertainty with the value that we calculated. State the measured values and the predicted values with their uncertainties in units. State your percent difference that you just calculated, and then say whether your values agree with an uncertainty. So is your percent difference smaller than the sum of the two uncertainties? State whether the theory is supported by your data, and then finally you identify what your largest source of uncertainty is. And you identify a largest source of uncertainty regardless of whether your values do or do not agree with an uncertainty. If the values do agree with an uncertainty, then your largest source of uncertainty will be something you took into account. So you go and look at your raw data values. Whichever measurement you took had the largest percent uncertainty, that would be your largest source of uncertainty when the values agree with an uncertainty. If the values do not agree with an uncertainty, then the largest source of uncertainty has to be something you didn't take into account. So something like friction or air resistance, or maybe the track wobbled or something. In general, pick one thing. If you give me a laundry list of everything it possibly could be, I won't give you marks for that. Choose the one thing you think is most likely to be your largest source of uncertainty.